tangent planes and linear approximations. Suppose f is a function that has continuous partial derivatives. An equation of tangent plane to the surface of z equals to f of x and y at the point x sub 0, y sub 0, z sub 0 is z minus z sub 0 equals to the partial derivative of f with respect to x at the point times x minus x sub 0 plus the partial derivative of f with respect to y at the point times y minus y sub 0. So this is basically the equation of tangent plane to the surface. For example, question says, find tangent plane to the elliptic paraboloid z equals to 2x squared plus y squared at the point 1, 1, and 3. So you have x, y, and z. You can indeed check to see if you plug in 1 and 1 into the equation of the surface, you end up with z equals to 3. So 2 times 1 plus 1 squared is 3. This is a two-variable function. F of x and y is 2x squared plus y squared. Now, let us take the partial derivative of x, partial derivative of f with respect to x, which becomes 4x. In this case, you're going to set y equal to a constant. So the derivative of 2x squared becomes 4x. If you plug in 1 and 1 for x and y, your rate of change with respect to x becomes 4 times 1 or 4. Now to take the partial derivative with respect to y, set x equals to a constant. The derivative becomes 0 plus 2y. When you plug in 1 and 1 for x and y, your rate of change becomes 2. So now let us take a look at our formula. Z minus z sub 0, which is 3, equals to 4, which is the partial derivative of f with respect to x at the given point, times x minus x sub 0, which is 1, plus the partial derivative of f with respect to y that we just calculated, which is 2, times y minus y sub 0, which is 1. If you simplify this, the tangent plane equation is indeed a plane. Z is equal to 4x plus 2y minus 3. Now let us take a look at visualization here. This is our elliptic paraboloid, as you can see, and the equation of tangent plane, which is 4x plus 2y minus 3, is tangent to the surface at point 1, 1, and 3. So linear approximation helps us to basically evaluate the function locally. The linear function whose graph is the tangent plane, namely L of x and y, equals to f of a and b, which is your z value at point A and B, plus the partial derivative of f with respect to x at A and B times x minus a plus partial derivative of f with respect to y at A and B times y minus b is called the linearization of function f at A and B. So you only have your x and y here. You can easily plug that into the function and find the z value. So any function locally can be approximated by its linearization, which is your z sub 0 plus partial derivative of f with respect to x times x minus a plus partial derivative of f with respect to y times y minus b. Also called the linear approximation or the tangent plane approximation of function f at point A and B. We have a nice theorem. The theorem says if the partial derivatives f of x and f of y exist near a and b, it means that we look at this locally and are continuous at a and b, then f is differentiable at a and b. Let's take a look at one example using linearization to approximate crazy-looking functions. In this example, you have x times e to the power xy. This function is differentiable at 1 and 0. Our goal is to show it that. And then we want to find the linearization there. Then we're going to use this linearization to approximate the function at 1.1 and negative 0.1 without using a calculator. Let us begin. The partial derivatives are, first of all, note that you have multiplication of two functions. So we're going to go back to elementary calculus and use product rule. The partial derivative of f with respect to x is e to xy, which is the derivative of the first function, which is 1 times the second function, e to the power xy, plus x times y e to the power xy, which is the derivative of e to xy with respect to y. Now, if you plug in 1 and 0, because the question says find linearization when x is 1 and y is 0, that's why we plug in 1 and 0 for our x and y. And as you can see here, you get e to the power 0, which is 1, and this guy disappears, which has y equal to 0 in it. So this guy becomes 0, and here you have e to the power 0, which is basically 1. Now for the partial derivative with respect to y, you're going to do the same thing, but please note that your x acts like a constant. So it is basically a constant times e to the power a constant times y. So this is basically x times x, e to the power xy, then plug in 1 and 0. You get 1 times e to the power 0, or just 1. Now the linearization is z value, which is f evaluated at 1 and 0, plus the partial derivative of f with respect to x at 1 and 0 times x minus 1, which is 1 times x minus 1. We just calculated the partial derivative with respect to x here, and we just plug that in here, which is 1. Plus the partial derivative of f with respect to y, which is 1 times y minus y sub 0, which is 0. So here we go. We just did some plug-ins and simplified as much as we could. This becomes x plus y. So from this crazy looking function, x e to the power xy, we end up with a nice linearization, which is x plus y. Why it is helpful? Because we can easily calculate this function, approximate this function without using a calculator. So if I ask you to find the z value of the function around 1.1 and negative 0.1, you just plug that in, 1.1 for x minus y, which is 0.1. This becomes 1. So this relation helps us to approximate the function nice and easy. This is the z value, approximated z value for the function. You could use calculator to check to see how this value is close to the z value that you have. If you use your calculator and evaluate function x e to the power xy, you see it is 0.98.